Hello everyone. Today's lesson is going to be very long because this is a very big topic on reaction kinetics. So we are going to cover a lot of content today, but I will just focus on important concepts and not every single learning outcomes. Okay, so we're going to look at what is rate of reaction, rate equation, how to construct rate equation and use it to determine the order of reaction and justify for zero and first order reaction. Okay, we are also going to look at what is half-life, how do we apply it in calculation, how to calculate rate constant, and touch on the Boltzmann distribution curve and relate how catalysts will bring about a lower EA through an alternative pathway and some applications of catalysts and enzymes. Now, what is reaction kinetics? It is the study of the rate of chemical reactions, which include the factors that affect them and the mechanism by which the reactions occur. So we're going to look at the speed of reaction, the calculations involving it. So the rate of reaction can be defined as the change in concentration of a particular reagent or reactant or product per unit time. So we can take the change in concentration of a reactant or product divided by the time taken to obtain the rate of reaction. And there are various units we use depending on the time. So it could be per second, per minute, or even per hour. Now, the rate of reaction is expressed as the decrease in concentration of reactant A per unit time or increase in concentration of product B per unit time. Rate is a positive quantity, okay? Now, so what is instantaneous rate? It is the rate at a particular time that is the rate at a particular instant during the reaction. So when we draw the graph showing the change in concentration of a reactant over time, okay, in order to obtain the instantaneous rate, we can actually draw the tangent, okay, to a point on the curve and calculate the gradient using rise over run. Okay, we can do the same for the change in concentration of product over time to obtain the instantaneous rate. The initial rate of the reaction is the instantaneous rate at time equals to 0. Okay, it indicates that at the start of the reaction, only a small amount of reactant is used up. So the initial rate is normally highest, normally, okay? Because at the start of reaction, we have the maximum amount of reactant present. So this is how we can use the graph to obtain the tangent at the initial rate. Average rate of the reaction during a specific time interval is the change in concentration of a reactant or product over that time interval. So we calculate the change in concentration of reactant over the time. We do likewise for the product. So it is like the total amount of reactant reacted over the total amount of time interval. So in practice, the initial rate can actually be approximated by the average rate, provided that the time interval is small enough and we start the time from time equals to 0. So the smaller the time interval, the closer is the value of the average rate to the initial rate. So this is the assumption made if we want to directly relate average rate to initial rate. It's a shortcut lah. So in a question, if the time interval is considered small, we can just directly take the average rate as the initial rate. Now, what is the relationship between the different rate of reaction? So the rate of consumption of A is equal to the rate of consumption of B equals to the rate of consumption of C equal to the rate of consumption of D. If we have this particular reaction, A plus B forming C plus D. Okay, so, and if we have this reaction with 1 mole of A reacting with 2 mole of B to form 3 mole of D, then we need to consider the mole ratio. So for rate of reaction, you can either take the change in concentration of A over time or 1/2. So since the mole ratio of B to A is 2:1, you need to divide by 2 to obtain the rate of reaction with regard to concentration of B. We also do likewise for D, where the mole ratio is 3:1. So it's 1/3 times the change in concentration of D. So in general, we consider the coefficient, and this is what we obtain. Now let's look at a word example. When dilute aqueous solution of peroxide disulfate and iodide ions are mixed, the reaction occurs. The iodine produced can be detected by adding a little starch solution to the reaction mixture, since a blue coloration is obtained when the iodine concentration reaches 1 × 10⁻⁻5 mole per dm³. Suppose the time taken for the blue coloration to be observed is 80 seconds at 25 degrees Celsius. Calculate the following: the rate of formation of iodine, the rate of consumption of the peroxide disulfate, and the rate of formation of sulfate. So looking at the rate of reaction equation, we can write in this manner. So we have -1/2. Why minus? Because the reactants are decreasing in concentration. Okay, same for the peroxide disulfate, S2OA2- as well. But for the products, it will be a positive sign. And if we considering the coefficient or the mole ratio for sulfate, we divide by 2. Now, so to calculate the rate of formation of iodine, we take the concentration of iodine, divide by the time taken, which is 80 seconds. So the answer is 1.25 × 10⁻⁻7 mole per dm³ per second. To calculate the rate of consumption of S2OA2-, okay, we use this equation, which is equivalent to this, which is the same. Rate of formation SO4(2-), because this time around, right, because it's half, right, so you need to times 2. For S2OA2-, we don't need, because S2OA2-, okay, there is no coefficient here, so you just directly take the value. But for SO2-, right, be careful. It equals to half of this equals to this. This one, sorry, this 2. So in order to find this, you times 2 to find the sulfate concentration change over time, the rate of formation of sulfate. It's a bit different. Okay, so be careful of that. Because this and this happen to have the same mole ratio, so they happen to have the same rate of consumption or formation, but it's not the same for sulfate with a different mole ratio. Okay. Now, consider this reaction A plus B forming product. Experimentally, right, we can see that the rate of reaction is related to the concentration of individual reactants using this equation. All right. So we have rate constant multiplied by the concentration of A and B, and A to the power of M. Okay. The order of reaction, same for this. The overall order of reaction, you just add up together. This is the rate equation. So defining the basic terms, right, it's important to know how to define this. Okay. Because there will be questions that ask what is rate equation, what is rate constant. So this question will be asked at national exam. So please remember, okay? So rate equation for reaction relates the rate of reaction to the concentration of each reactant raised to the appropriate power. So to obtain the rate equation, we can get it from experiment, and we can't deduce it from theoretical or from the stoichiometric equation. Cannot. You must obtain the rate equation from experimental data. Okay, and it may not include all the reactant, because if this reactant have the order of reaction 0, then it will not be included in the rate equation because it is not affecting the rate of reaction. So it may not include all the reactants. Okay. For rate constant, this is the definition. It is the constant of proportionality. So the symbol for the rate constant is K. Then the units will depend on the overall order of the reaction. And K is constant for a given reaction at a particular temperature, and the value will increase with increasing temperature or in the presence of a catalyst. So the larger the rate constant, the faster the reaction. So K is affected by temperature, okay, or catalyst. Now, order of reaction with respect to a given reactant is the power to which the concentration of that reactant is raised in the rate equation. So if the coefficient is 2 or the mole ratio is 2, then the order of reaction with regard to that particular reactant will be 2. Okay, so the order of reaction can be determined experimentally from data also. And it shows the exact dependence of the rate on the concentration of a given reactant. And this order of reaction, right, may not be a whole number. It can also be a fraction, even positive or negative. The overall order of reaction is the sum of the power of the concentration. For example, we have this example, P raised to the power of 1, Q to the power of 2. The overall order is 1 plus 2 equal 3. So that's how you can calculate. To interpret the rate equation, this is how we can interpret. So if m and n is 0, according to this equation, all right, then a to the power of 0 and b to the power of 0 will just give you 1, and the rate will be equals to the k. And the units of k will be the same as the rate, mole per dm cube per second. So in this case, right, both a and b are not affecting the reaction rate. They are independent, meaning the reaction rate and the concentration of A and B are independent of each other, since the order of reaction for both reactants is 0. So this is a 0 order reaction. So even if you change the concentration of A and B, it will not affect the rate of reaction. Okay. Now, what happens if you have m as 1 but n keep as 0? Now, in this case, the rate will be equals to k times the concentration of A raised to the power of 1. So this is a first order reaction, and it's first order with respect to A and 0 order with respect to B. Okay? And this reaction equation, right, rate equation shows that, okay, if you double the rate, right, then you double the concentration will double the rate. So rate is actually directly proportional to the concentration of A. So the relationship is directly proportional. If you have both reactant raised to the power of 1, then this is a second order reaction because it's first order with A and also first order with B. And the units of K will change accordingly. Okay? Now, for the derivation of the units, you can try yourself to obtain. Rate is mole per dm cube per second, and concentration of A is mole per dm cube. So this is how we get the units of K. Same for here. Now, if the concentration of A double, rate will be double. If B concentration double, the rate double. If both A and B concentration double, the rate will be times 4. Okay, so just take note of that. If let's say it's 0 order with respect to A, but second order with B, then in this case, right, you double the rate, sorry, double the concentration, U times 4, okay, the rate. And you can derive the unit accordingly. Now, for this question, right, what information can we gather? So based on this, right, we can actually calculate to see whether units of K is indeed this. So upon calculation, upon verification, is not. But it's obvious that it's definitely a second order because the concentration of the two reactants are raised to power 1. Okay. C is conceptually wrong. K is dependent on temperature and catalyst, not the reactant's concentration. And D is also wrong. You can't say that this is true because it is not second order with respect to iodide. Another example, okay, the reaction between bromine and methanoic acid is first order with respect to both bromine and to methanoic acid. What information can you gather from this equation? Okay, so if you double the concentration of methanoic acid, will double the rate. So you must first construct this rate equation to see clearly. So the strategy to do this is to first construct this rate equation of the reactant, take into consideration the coefficient, which is the mole ratio, and then conclude this. If you double the concentration of methanoic acid, would it double this? Okay. If we base on this, right? Yes. Assuming that Br2 in statement 1 concentration is kept constant. Okay. Because in the question, they already say first order here. You cannot, okay, I need to warn you, you cannot write this based on this alone. This has to be derived by experiment data. So there could be a question that say, if they write this, then they never give this, right? They say this is the equation, it is correct. It's not correct because you cannot use mole ratio directly to construct the equation. You have to use data. But in this question, the data is assumed to be taken and you just have to accept that it's first order based on the given question because data was not given. So this is the conclusion of the data. So this one, right, will be true if the concentration of Br2 was kept constant. So this is true. Okay. Halving the concentration of both reactants simultaneously will halve the reaction rate. So if you half, it will be 1/4. So it's not true. If you halve both, then the reaction will be 1/2 times 1/2 equal to 1/4. Okay, so how about the overall order? The overall order it should be 2, 1 plus 1, because it's first order with respect to bromine and methanoic acid. So you can sum up the order of reaction. Now, let's look into the details of first order reaction as well as half-life. So first order reaction is one in which the reaction rate is directly proportional to the concentration of a single reactant raised to the power of 1, like this. So yes. So consider the first order reaction, okay? So I just want to repeat, right? You can't use the equation to deduce M and N, cannot. Okay, you have to use experiment data. So this is derived by experiment data, not from any equation, correct? Okay, so just take note of the units of rate constant. And then this is the definition of half-life. Please remember the definition, they will ask sometimes. The half-life is the time taken for concentration of reactant to decrease by half its initial value. Okay, so based on, there's some derivation, you don't have to know how it's derived. The half-life is constant for first order reaction, and you can calculate half-life by taking log 2 over K by a mathematical equation. Okay, this is actually derived from mathematical equation. Okay, no need to know how to derive. Okay, so this is the equation. So if you know the rate constant, you can actually determine the half-life, or vice versa. You know the half-life, you can find out the K. So half-life is independent of initial concentration. This is only for first order reaction. So regardless of the initial concentration, half-life will not change. However, for other orders, right, please take note that half-life will change. So for first order reaction, right, these are the associated graph to take note. You'll be asked to sketch and apply your understanding. So for the first one on the left, we have rate against the concentration of reactant. So if it's first order reaction, we will expect the relationship between them to be directly proportional, as what we have concluded here. Okay, directly proportional. Now, if that is the case, we will obtain a graph with a straight line passing through the origin having a positive gradient. Okay, if we take the concentration of reactants against time, we will have something like this. Okay, now from the graph, the first half-life is the time taken for the concentration to reduce by half. So we have C0 as the initial concentration. So the half-life is the time taken for half of it to decrease. So as the reaction progresses, half of this, which is 1/4, okay, will decrease because it reacted to form the products. So another half gone, another half gone. So, and for first order reaction, right, T1, T2, T3 should be equal. So if your time taken for every half or subsequent half of the concentration will decrease, right? Then if that half-life is constant, then it is a first order. So this is important. So if you look at a graph and it happened to have this relationship, you can conclude that, hey, this is first order. Okay, another graph shows the first order reaction of the concentration of product against time. So from the graph, the first half-life is the time taken for the product to increase from 0 to half. So it is just the opposite of the reactant in a way. Okay. Then for the other half to reach 3/4, meaning you times half of this. Okay. Then you plus this one, you will get 3/4 because half of this is 1/4. 1/4 plus this give you 3/4. All right. So this is how it was calculated. So this was calculated by taking half of the initial concentration time plus another half. So you have 1/4 plus half. Okay, then you have 3/4. So that's how 3/4 is obtained. Repeat the same thing for here. So once you obtain 3/4, you take half 3/4 plus 3/4, and you will get 4 plus 3. So you have about 3 half times half times 3/4. So at 3/8 plus 3/4. So you have times 2, 6, 9 over a bit too much, right? Times 2 times 2, 6, 6. No, it should be to get 7/8, right? Is take. So this is correct. Half times half, 1/4 plus half. Then you have 2 plus 1, 3/4. Then this is for. So, okay. T3. So I need to equate also, right? Okay, so is you gain another another half. So you have 3/4 plus this. Do I correct this? Oh, this one is from here. So you just take 1 minus 1/8. I think that will be easier to see. Okay. So you calculate how much you drop, then you just take 1 minus. Yeah, it's easier to see in this way. Yeah. Rather than calculate directly because it's the opposite. Okay. Now, this is the word example. The decay of radioactive isotope follow first order kinetics. If the rate of decay of radioactive isotope decreases by 200 counts per minute to 25 counts per minute after 24 hours, calculate half-life and then rate constant at 6 unit. So you can actually use you can just use this method directly. This is more direct. 200, drop to 100, drop to 50, and drop to 25. So how many half-life it takes? 3. So the half-life, so it takes how long to reach here? 24 hours. So 3 half-life give you 24 hours. So 1 half-life give you 24 divided by 3, 8 hours. So that's a faster way to obtain the answer. So once you obtain the half-life, you just use this equation, ln 2 over k equal half-life to get k. And make sure you know the units lah. It's actually just hour to the power of -1. Okay, another example is you have 2 isotopes with half-life of 5 minutes and 15 minutes. Experiments start with 4 times as many atoms of P as Q. So this is a first order reaction. How long will it take before the number of P left equals the number of atoms of Q? So you can take, you can start with, since they already mentioned, right, P is 4 times as Q, right? So you start with 4x, okay? So 4x become 2x, become x, become half. So 15 minutes to reach half. As for Q, right, you take just 15 minutes because the half-life is longer. Okay, 15 minutes to reach half. So if you look at P to reach here, it will take about 15 minutes long. Now, another example, you have this first order reaction X forming Y, and it says that the half-life is 30 minutes. So after 100 minutes, what is the fraction of X remains? So you can let C0, use algebra here, be the initial concentration of X, and C equals to concentration of X at a given time. So you can just use this method. C0 reduced by half, become half C0, another half, 1/4, 1/8, and yeah, a bit like mathematics method lah. Then so you can see that, hey, in order to, so after 100 minutes, so it's just 33 half-life, which is 90 minutes, right? All right. So time taken for it to drop to, let's say, 1/8. Okay, 1/8 which you can see that is related in this way. You can see a pattern, 1/2 to the power of the number of times of half-life. So C equals to 1/2 to the power of 3 C0. And to calculate, you can use this. So this is the understanding lah. And for the solution, right, you can just take 100 minutes. So you understand, divide by 30 to get the N. Okay. And then, so N is 10/3, which is taken from 100 divided by 30. Okay. So C over C naught, okay, you can tell that it is 1 over 2, which is half-life to power of n. Okay, then 1 over 2, you can just take to power of 10 over 3 to find the fraction of x that remains. So because 100 mini is not a very nice number, so you have to use this method to get that fraction. Okay? Okay, let's take a look at this. So the time taken, right, is equals to n. So this is, you can tell from here, right, the time taken is equals to 3 times the half-life. Okay, and the concentration is equals to 1 over 2 to the power of 3 C naught. So you can make this conclusion here lah. Yeah. Okay. Now, okay, let me take out this thing. Okay. So what is second order now? So we have done with first order and what half-life is. We move on to second order. Second order is one which the reaction rate is proportional to the product of the concentration of the two reactants. Okay, so it is directly proportional to both A as well as B. Okay, both of them. Or it could be that the rate of reaction, okay, is proportional to only one of the reactant, but this reactant, right, is raised to the power of 2. It could be that also, because order of reaction can be either both of them or just one of them. Then the other is zero order. It could be that. So, assuming we have these reactions where 2A becomes the product, so the rate of reaction is equals to K times concentration of A. And this is the units of rate constant. So the graph associated is as follows. So if that is the case, right, then rate, as concentration of A increase, the rate should increase exponentially. Should increase at an increasing rate, right? The rate should increase at an increasing rate. If we plot the graph of rate against A to the power of 2, then it will be a direct proportional relationship. But if it's reactant against time, it will be something like this. But the half-life is not constant. We have a longer half-life in the second one. So as the reaction proceeds for second order, we will notice that the half-life gets longer and longer. For zero order reaction, the reaction rate is independent of the concentration. We did mention that. And these are the units. So for the graph will be something like this. Since rate is equals to K, that's it. As for concentration of A, it means that, the gradient K is actually constant and it should be decreasing if you talk about reactant. For product, it should be increasing starting from origin. Now, so you can see that is a difference between first, second, and zero order. First and second, you have something like this. If you recall first order, yes, reactant against time, or like that, but its straight line will be zero order. Based on this mathematical relationship here. That's why it's like that, because the gradient is constant. Now, for pseudo order, right, there are 3 situations to consider. Number 1, the presence of a large excess of reactant. So consider this reaction where the rate equation is as follow. So if let's say, right, the initial concentration of S2O82 minus is very, very high as compared to iodide. Okay, so the S2O82 minus concentration will hardly change. In any case, right, in this case, right, the S2O82 minus may be regarded as effectively constant. Okay, so at all times, right, this concentration will be equivalent to the initial concentration. Because it's so high, okay, there will be little negligible change lah. Yeah, throughout the reaction. So the rate equation can be just modified as rate equals to K. Approximately means you consider the S2O82 minus. So it becomes a constant times the concentration of iodide. Remember, it's not a 2 here because we haven't done the experiment to see the order of reaction yet. So in this case, the reaction has a bit pseudo first order kinetics. And this is a pseudo first order rate constant. Okay. Now consider a reaction like this where the rate equation is rate equals to K times this times this. So if the B, right, is present in a large excess, okay, very, very significant amount, okay, a lot, then we can just consider concentration of B to be constant and rewrite as follow. So this reaction actually has an overall order of m plus n, but appears to have m because the concentration of B is very high, is in excess. So we call this pseudo. Pseudo means by right it's not first order, but because of this condition, it is like first order, so it's pseudo. Now, case number 2, the reactant itself is the solvent. Let's say we have the hydrolysis of ethyl ethanoate, okay? The rate equation is as such. So water is used as the solvent, and because solvent, so it is present in large excess. So the concentration will remain largely constant throughout the reaction. So the rate equation can be modified as rate equals to the K constant, you consider water there, then equals multiplied by the concentration of the ethyl ethanoate. Okay, you can write like that if the reactant happen to be a solvent. If let's say there is a catalyst like this reaction, hydrolysis of sucrose in the presence of hydrochloric acid, you can write the rate equation as this. All right. Now in this case, right, HCl is a catalyst. So it will increase the rate of reaction, but it is not consumed. All right. So it participates, but it is regenerated. So consequently, the concentration of HCl is regarded as essentially constant during the reaction. So the rate equation can be modified as rate equals to K not sucrose, because HCl itself is a catalyst. It will keep on regenerating. Okay, so these are the 3 conditions for pseudo first order to occur. Okay, so this is a summary. You just read through yourself. It's a summary of what we have gone through. Now, the next part is to find the order of reaction. So in studying kinetics using initial rate method, the initial rate is first determined by measuring the change in concentration of the reactants or products, which occur in the first small time interval after the reagents are mixed. So the order of reaction with respect to reactant can be found by comparing the initial rate of reaction at different known initial concentration. So there are 2 approaches to compare initial rate, either by inspection or calculation. So how do we do it? So let's say by inspection, we can just look at the data of this particular reaction. So let's say this question asks, okay, determine the order of reaction with respect to each reactant. Now, so we can see that by inspection, right, when the concentration of X multiplied by 2, when this, let's look at Y first, easier. When this is constant, this one times 2, this one times 2. So in this case, right, when Y concentration double, initial rate times 2. Can you see that? Times 2 here, times 2 here. So the order of reaction with respect to Y must be 1. Then you look at X, right? 2 and 3. So we already know Y is rate of order of reaction is 1, right? So if this times 2 here times 4, it means that the order of reaction with respect to X will be 2. Because when the concentration of, because this is constant, but this one times 2, here times 4, right? So the order of reaction is 4 divided by 2, 2. Can this by inspection, a faster way? Okay, I like inspection method because it's faster to get my answer. Okay, unless the question in the structured section demands a full working with using the calculation method. Okay, but if they never specify, you can just use this method, which is much faster. So the rate equation is just this. The order of reaction is just 1 plus 2, 3. Then the rate constant is just take the rate divided by the concentration of the reactants raised to the appropriate power to get this. If you use calculation method, right, then that is when they demands you to, I mean, if they specify lah, then you can actually present this manner as well. You can take the rate of experiment 2 over rate of experiment 1, okay, which is you take K, so you use this general equation 0.02, okay, to power of m, then 0.02 power n, then the same thing 0.01 power m, 0.01 power n. The order of reaction should not be changed, it should be constant, equals to 0.04 over 0.01, then you just use math, cancel the K. This one can come together, right? Become 0.02 divided by 0.01, gives you 2, right? 2m. Then you have 2n, so 2m plus 2n is something like this lah. So you have K cancel off, then you have 2m, then here should be 2n, then you can just, because they have the same base, you can just equate them like this, math. You learn that under indices, right? And then it's equals to 4, and then you change to 2 to power 2, so 2 n plus n equals 2, 2, so 2 equals to n plus n2. Then you take another 2 sets of experiment data, 3 and 1 this time around, to do the same thing, and you form another equation. Then it's simultaneous equation lah. Then you can solve it accordingly. Okay, that's a bit tedious lah. All right, but you can just use inspection to do this as well, which is actually faster. Okay, so but in this case, right, because you see it is for this one inspection, because it will be harder, because you can see there is no data that show that it's constant. You can see that, yeah, so that is the problem. So sometimes calculation might be better, don't have to think so much. But if you read by inspection, right, you can see that here times 4 when this one times 2, this one times 2. Okay, then if you look at this set of data, okay, there's no constant value between 2 experiment set. When this one times 2, this one times 4, then this one times 8. So it will be 1:2. I mean, order of reaction is 1 for each lah. Yeah, another way to look at it. Okay. Okay, moving on to the next question. So we have this equation where A undergoes decomposition. So this is the kinetics. So again, they will provide you the data to determine the rate equation and the order of reaction. Okay, that will be necessary. So you're supposed to use a graph. Okay, this time around we do for you. So you draw, not sketch. Draw a graph of concentration against time. Okay, time is normally the x-axis lah. Okay, then you will get something like this. Then the question asks, okay, find the rate equation. So how should you do? Find the half-life law to see whether it's first order or second order law. So from the graph, it can be seen that, hey, the time taken for A to drop from 0.05 to 0.025 is around 48 minutes. From 0.0 to 0.04, okay, another half-life to 0.02 is also 48 minutes. Okay, so you see, if you take any, you take any time difference, right? Okay, it will still be the same half-life, right? It means that half-life is constant, it means that order reaction is 1. Remember that, if half-life is constant, it's first order. Half-life not constant, second order. If it goes straight like this, it means K is constant, right? Then it's 0 order. Okay? So the rate equation is just K to respect of A. Of course, only one reactant, raised to power 1. To find the value of rate constant, you just take use a formula, K equals to ln 2 over half-life. That will be faster. Don't think about using the equation, forget it. Okay. Because you can't use the rate because you only given a time. Yeah. So it's faster using this method. Another word example. So normally this topic has a lot of graph. Okay, you have this reaction P plus Q forming R and S. So the kinetics of the reaction was studied. So the result from 2 experiment 1 and 2 was shown. So in each experiment, right, the concentration of Q can be regarded as effectively constant. Okay. So Q is constant. All right. P is the one that is changing. So plot this data on a suitable axis and use your graph to determine the half-life, the initial rate, and construct the rate equation. So in this case, right, you're plotting a graph of concentration of P against time. You'll just plot for first experiment, plot for second one. Do it fast. Okay. So consider the first graph, right? The time taken for concentration of B to drop by half. Correct? Means 0.01 drop to 0.05. You say how much time? It's 116 minutes. You take another half-life, it's still 116 minutes. So the order of reaction is 1. This is what they say, use the half-life method. Then they ask the next question. Then you use initial rate method. So you cannot use the half-life method for Q. So use another method. So what you can do is that you can actually obtain the gradient of the tangent. Okay. So you take, for experiment 2, you plot the tangent and you get something like this. So they take about maybe 84. They never showed it. I never showed it here, but yeah. And then you get this. Then consider the graph. For experiment 1, experiment 2, I do for both. Then you get this initial rate respectively. So this is the rate. So you can see that when the concentration of Q, right, times 1.5, the rate also multiply by 1.5. So its order of reaction is Q. So you're trying to get it is, yeah. So this concentration is like, 1.5 of this. So if the rate is 1.5, then then it is first order. It will be easier to draw the tangent at the initially time equal to 0. This is easiest. Should be the way. Then you construct a rate equation and calculate rate constant. Very standard question actually. So rate equals to K times concentration of P times concentration of Q. And then you can just use the data from experiment 1 directly. Any one of the data. Then just plug in the concentration of P and Q respectively. And you get the K and also the units as well. Okay, units, be careful of the units. Okay, now so you have to like calculate the unit separately lah, like to get this. Okay, to get this right, you have to take mole rate is, then this is 2 concentration, right? So you take mole dm cube to power of 2, then equals to mole. So you have to do a separate step, like if cannot do it so quickly. Okay, so it will be 1 minus 2 give you minus 1, minus 3 plus 6 give you plus 3. That's how you obtain the units for K. Okay, okay. Okay, we're going to study kinetics of various clock reactions to understand better the applications, how we can apply it in different experiments or reactions. Now, so in studying kinetics using initial rate method, the initial rate is actually approximated by average rate. I mentioned that earlier. So if the time interval is small enough, this estimation is a good one. So in practice, the average rate of reacting a fixed concentration of reactant or forming a fixed concentration of product is measured using this thing called clock method. So what is a clock reaction? So certain reactions are accompanied by prominent visual change like a precipitate forming, or there's an obvious change in color. So we can study the rate of reaction by measuring the time taken for this prescribed visual change to occur. So if there's an apparent change, right, we call this the clock reaction. So for example, this reaction between thiosulfate and hydrogen ions, okay? You can either represent it in chemical equation form or ionic equation, both are fine. So when sodium thiosulfate reacts with acid, there is a yellow precipitate of sulfur. So this S is appearing as yellow, it's a yellow precipitate. Okay, it will form a suspension. And the rate of reaction can be studied by the method of initial rate. So in this case, right, the initial rate is approximated by average rate. So in this experiment, the time taken for a fixed amount of sulfur to form can be measured. So we usually measure the time taken for enough or sufficient sulfur to form to obscure the black cross that was drawn on a piece of white paper below the beaker of the mixture, okay, of the reaction mixture. So we have a cross, and then we place the beaker on top of the cross, and then we mix the solution to form the precipitate. Okay. So once the cross is obscured by the formation of the precipitate, then we can stop the time and measure the time taken for this fixed amount of sulfur. So we assume that to obscure the cross, it requires a certain amount of sulfur to obscure it. And we can measure the rate of reaction from there. Now, so this is experiment data. So we have the volume of the respective reagent as well as water and the time taken. So rate is directly proportional to 1 over time. So we just take the time reciprocal all of them to find the rate. This is not rate, this is directly proportional to rate, okay? Anyway, we are only interested to find the ratio and not the absolute value, okay, to make the comparison. Why is the volume of water varied? Okay, now we need to keep the total volume of the reaction mixture to be constant so that whatever concentration of the reactant is there in each experiment, it will be directly proportional to the volume used. So the concentration, right? So the volume of the reactants, okay, is directly proportional to the concentration. Okay, so for example, to calculate the initial concentration of sodium thiosulfate, we can take the amount of sodium thiosulfate divided by the total volume. So the amount of thiosulfate is calculated as volume multiplied by concentration. Okay, so we keep this constant, and by doing so, right, so we know that, okay, the initial concentration of thiosulfate is this, equals to amount of sodium thiosulfate divided by the total volume. So that's how you can calculate the concentration. And the amount is mole, so mole equals to volume times the concentration. Okay, divide by the total volume, give you the concentration of thiosulfate. Correct? So if we keep this constant by adding different volume of water, okay, so what happened is that what changes is the volume of thiosulfate, S2O3, right? So this will change, okay? So if this is constant, because every time you add the sodium thiosulfate, you must understand that it's the same concentration. So this is constant, this is constant. So the concentration of thiosulfate is directly related or proportionate to the volume. It's proportionate to this, because these two are constant, by the way. So every stop you put in, right, it will be constant, because you're taking from the same place, correct? Now, so because of this, right, the initial sodium thiosulfate concentration is directly proportional to the volume of the sodium thiosulfate. So this is the model answer, why you keep the volume of water changing, because you want to keep the total volume constant so that initial concentration is directly proportional. So must write these two, okay, to demonstrate the full understanding. And then the initial concentration of thiosulfate is proportional to the volume. So initial H plus concentration is also proportional to the volume of acid. So something like that. So what is the relationship between the rate and the time? So rate is inversely, not equal, inversely proportional to time, since the amount of sulfur produced is kept the same. So in this case, right, the factor that changes this time must be concentration of the reactants. Okay? Since we assume that it's the same amount of sulfur to obscure the cross. Yep. So why is this directly proportional to each other? Okay, so the initial rate of formation of sulfur is approximated by average rate. Remember that if the time interval is assumed to be small and measured from 0. So if that is the case, so average rate is equals to change in amount of sulfur over a regular time interval. Okay, x minus 0 over t minus 0, so x over t. So in this case, x, right, is the amount of sulfur. So we assume that, okay, it's the same amount of sulfur to obscure the cross. Since x is constant, so we are talking about same cross, same beaker, same depth, right, of solution, correct? So the x will be constant, but in that case, rate is directly proportional to 1 over t, but they are not the same. Now, so how do we process the results? So if we look at the data again, comparing 1 and 2, keeping this constant and this one divided by 2, the volume, so that the time taken is times 2. So in this case, right, comparing experiment 1 and 2, right, when V2 double, 1 over T double, correct? So the rate is directly proportional to the concentration of sodium, the thiosulfate ions. So in this case, it's by inspection. So order of reaction is 1. So as for HCl, do you notice that for HCl, right? Let's go to the data. Keeping this constant, this times 2, this one never change, never change much. So 0 lah. So it is rate equation is just this. So HCl is power of 0, so it's 1. So you don't write it down. Now, another example is hydrogen peroxide reacting with iodide to form iodine. So this is also a clot method. When a small but constant amount of sodium thiosulfate is added to the reaction mixture, so what happens is that the iodine being formed, right, will react in a second reaction. So the iodine, right, will react with thiosulfate, redox reaction. So iodine is reduced to iodide. And because reaction 2, right, is much faster than reaction 1, so the concentration of iodine, right, will actually be effectively 0. Yeah, as long as there's some thiosulfate ion in the mixture. So because reaction 2 is so fast, right, as long as there's this S2O3 2 minus present, you can regard iodine not present because it will quickly react to form iodide. So at this point, right, when the small amount of S2O32 minus is like, completely used up, only when this is completely used up, right, the reaction 2 will stop. Okay, but reaction 1 will then continue. Then the free iodine, I2, from reaction 1 will be present. So this iodine, right, will cause a sudden appearance of blue-black color if you add starch previously. So because the blue-black coloration appears because of the starch-iodine complex. So if you carry out the reaction in the presence of small but fixed amount of sodium thiosulfate and starch indicator, you introduce a clock. The clock tells us like, when a given concentration of iodine is formed. So with a certain amount of iodine formed of certain concentration, it will form the blue-black color. It's like a clock, ding, ding, okay, like that. So a series of experiments was carried out using different volume of the 5 reagent and the solution being made up to the same total volume with appropriate volume of water added. So the volume and amount of sodium thiosulfate was kept constant for each experiment so as to ensure that the amount of iodine produced was constant for all experiments. So this is the experimental results okay? So here are some questions to ask when analyzing the data. So like, how is the rate measured? Why was the total volume kept constant? What is the relationship between initial concentration of reactant and the volume used and the relationship between initial rate and the time? Okay, so let's start off with this. So what is the relationship between the time taken for the blue color to appear and the initial rate of reaction? Okay, so the initial rate of reaction is actually inversely proportional to the time taken for the blue color to appear. So initial rate is directly proportional to 1/T. Okay, how do you relate to the, so this is how you do it. So initial rate of reaction is equals to initial rate of formation of iodine. Since time is small, measured from 0, initial rate is equivalent to average rate of formation of iodine. Okay, then X is just the time taken, is the concentration of iodine formed when the solution turned deep blue, and the time is for the appearance of the deep blue solution. Okay, since all the reaction mixture contain the same amount of sodium thiosulfate, you assume each reaction mixture will turn deep blue only when it produces the same concentration of iodine. So X has been constant in all the experiment. So since X was kept constant, initial rate is directly proportional to T. So we have to make all these valid assumptions to make this conclusion. Now, how do you determine the rate equation? Since the total volume was kept constant, okay, and since the same amount of sodium thiosulfate was used, okay, and the same concentration of iodine was produced when the solution turned deep blue, initial rate is directly proportional to 1/T. So if you compare the experiment, comparing 2 and 4, when you double the volume of H2O2, hydrogen peroxide, 1/T was doubled. So the order of reaction, right? So you double this. This one is also double. Can you see that? So by inspection, provided the other variables were kept constant, you must check, no change, then you can actually relate one to another. So the order of reaction with respect to H2O2 is 1. So for potassium iodide, right, it's the same thing. If you go to there, potassium iodide inspection, potassium iodide, okay, here, the rest constant, 2 and 3, this one times 1.5, this one times 1.5 also, right? So same So rate and concentration of iodide is directly proportional. Okay, they are. Because rate and 1/T direct proportional, volume, concentration direct proportional, they are. So you have to make all these assumptions to get your marking point. Then for the last one is H plus. H plus here. H plus, right? The thing is, right, you already know that, okay, peroxide is already order of reaction 1, right? So when this divided by 3, this one divided by 3, it's not because of H, but it's because of H2O2. So this is the understanding, you know what I mean? So because you can, from inspection, you really can see that from the first data, experiment 1 and 2, you know that H2O2 is first order of reaction with respect to it. So this one divided by 3, here divided by 3. So HCl got no effect. Yeah. Another way to do it is you compare 1 and 4. Then you do the equation. Okay? So you can use the equation. So knowing that this 1, 1, then you just, calculate. But I think my method is actually faster. Okay. Now, the other method, inspection, faster to get answer. Now, to study kinetics of a reaction, which is to measure the reaction rate and determine rate equation, we need to be able to monitor the concentration of reactant or product at various times as the reaction proceeds. So the choice to which reactant or product to monitor depends on which species in this reaction can be easily yet accurately analyzed. So for example, we have these reactions. Something that's easy, like you can do like, like the first one can actually use titration against KMnO4. We can observe the color change. Or this one, where you can titrate against sodium hydroxide using titration. Yeah, and as long as you can use titration, that would be fine. Yeah. So general procedure, right, for doing so is, or make sure you know how to do this because it may come out in the planning to study kinetics. Yeah, it seems difficult, right? Difficult means it may likely come out. Okay, not so straightforward. So the general procedure to do this is, number one, you start the reaction by mixing the reactants and start the stopwatch simultaneously upon mixing them. And then after that, right, using a pipette, an adequate portion, meaning a fixed volume of a sample, is withdrawn at a suitable time into another conical flask. Then at a certain time, the reaction in the withdrawn sample, right, is slowed down or halted effectively by adding a large volume of ice cold water, which help to dilute the mixture. Or you can add excess suitable quenching agent, which is either one of the reactants or catalysts. So the reaction in the withdraw sample has to be halted so that its composition does not continue to change before the titration. So the concentration of either the reactant or the product formed at time t1 in the reaction can be determined by carrying out titration of the quench sample. Then after that, right, you repeat step 2 and 3 at other timing to get the different volume of the titrant. Okay? So the sampling, quenching, titration step are repeated at suitable time interval, and you plot a graph of volume of titrant against time. So the graph plotted can be used to determine the order of reaction, as well as the instantaneous rate at any specific time by drawing the tangent and determining the gradient. Okay? So you must carry out titration. Okay? Yeah, it's like work backward. So use this result to find this, then find this, something like that. Okay, so another method is measuring the color intensity at regular time interval, which is actually quite direct, this method. Provided one of the reactant is colored, not color cannot do. So, and the concentration should be directly proportional to the color intensity to make this planning successful. So the progress of the reaction is followed by measuring the color intensity or adsorbent of the reaction mixture at regular time interval, measured using a calorimeter or spectrophotometer, either one of it. The rate of reaction can be determined from the change in color intensity over a specific time. So the measured color intensity values can be used to determine the concentration of the color species at various time intervals using calibration curve. Okay, so examples of reaction which rate can be studied by calorimetric method is those that have a color change, like all this. Another way is to something that you learn at O level, measuring the volume of gas at regular time interval. Okay, something like this you've done before, using the calibrated gas strange to measure the change in volume over regular time interval. So let's say for the decomposition of hydrogen peroxide, you can actually study the kinetics by measuring the volume of O2 gas over time in a graduated or calibrated gas stream, and the volume measured at regular time interval during the reaction. So you can plot a graph of volume of O2 against time, and then obtain the rate of reaction at any instant, which is the gradient of the tangent to curve at any instant. So from the graph, you can determine the order of reaction by checking if half-life is constant. Okay? Now, or you can actually take the change in volume also can. Either you measure the volume of gas directly or you measure a change in volume, but the graph will be different. It will be a graph with a decreasing gradient, moving downward. The graph is negative gradient in that case. Okay, you can also check the half-life as well, which is actually easier to get the half-life in this method. Another method is to just measure the electrical conductivity at regular time interval, because some solutions have ions, and ions are mobile charge carriers, so they will affect electrical conductivity. So what you can do is that you can measure the electrical conductivity over time, over regular time interval, by inserting electrodes and connect it to the conductivity meter, like these reactions here. All right, because the product form have less mobile ions, so there will be a drop in the electrical conductivity. Or you can measure pressure, which must involve gas So you can measure the total pressure, okay, in this method. Okay, so for example, for this example, right, NO2 becoming N2O4, right? So initial pressure, there's initial pressure, but there's change in partial pressure. So because it's 2x, so minus 2x here plus x, so PO minus 2x, x. Okay, this is called the ICE method, which I will teach you later in the next topic, equilibrium. So at time t, okay, so PT is equals to P NO2 plus PN2O4. So you take this plus this, you have PO minus X. So X equals to PO minus PT. Yeah, you shift the equation over here. And PN2O4 is equals to X equals to P naught minus PT. Okay? Yeah. So X is the partial pressure of N2O4 at equilibrium. Okay, then pressure of NO2 is just the initial pressure minus 2 times X, which is P naught minus PT. Then it's about 2 PT minus P naught. So something along that line. Okay, so we can actually use this method as well. Or so you measure the rate of reaction by determining the change in partial pressure of the reactant over time. Okay. Other examples you can use, and this is a summary. So this is the summary of the procedure. Yeah. Then the experiment technique. Yeah, basically this part is quite straightforward. Then this part, the chemical method, is the focus. Yeah, so what happens is that you have a continuous measurement of concentration of A at various time intervals by sampling, quenching, and titration. And then the titration result is related to the concentration of reactants and products. Then you plot a graph of volume or concentration of reactant against time, like this one. The first method here, the general procedure for sampling, quenching, and titrate metric analysis. Okay, so you run the reactions, okay, and then you actually pipette out a certain portion at a suitable time, okay, and then you use pour or add quenching agent, and then whatever remains, correct, you quickly run a titration. Then you determine the volume of the titrant needed to react completely with it, meaning there's a color change, okay, at different time. So you take different time, different, different time, different volume. Yeah, then you plot a graph, okay. So this volume is the volume in the burette that is used to not neutralize, but react completely, because it could be a redox reaction, may not be neutralization all the time, may not be. Okay. Okay, now let's look at reaction mechanism. So let's study reaction mechanism. So there are some terms and definitions to bear in mind. What is reaction mechanism? It is the collection of elementary steps in a proper sequence to show how the reactant particles are converted to product, which explain how reaction takes place. Elementary step is a distinct step in the mechanism which describes a single molecular event that involves breaking or making bonds, such as one reactant particle decomposes or two reactant particles colliding and combining. An elementary step is an elementary step. It cannot be broken down further. The molecularity, right, is referred to the number of reactant particles taking part in the reaction. So if you have unimolecular step, there's only one reactant particle. Bimolecular step, two reactant. Termolecular, three. Okay, but this is extremely rare, so we focus more on the first two here. Intermediate is a species found in one step, meaning let's say the reaction involves a few steps, right? Step one, step two. So this intermediate refers to the species, right, that appear in the step one, but is quickly consumed in step two, or may not be quickly consumed. It will just be consumed and you will not find it at the end of step two. Okay, so you normally don't represent it in the stoichiometric equation because it's not there at the end of step two. Okay, it doesn't appear in the rate equation and may be isolated for a short duration during the course of the reaction. So for example, right, NO3 is one example, which is the intermediate. So NO3 is the intermediate. Okay, now a single step reaction, right, is a reaction that takes place in a single step, meaning, okay, let's say this reaction, right, is only one step, then it's elementary. So some reactions are like that, only one elementary step, and the reaction mechanism is identical to the stoichiometric because it's only one step. So the stoichiometric equation is identical to the reaction mechanism, and you can deduce directly the rate equation. Okay, so let's say A become 2R, then the reaction mechanism is the same, is unimolecular, right? Unimolecular means one species involved, one reactant particles. Okay, so it's like that. You can just derive it if it's just elementary step lah. Okay, same for here. This bimolecular, so you can derive it like that. Okay, but of course normally is by data. But in this case, right, if it's single step, then we can just directly derive the rate equation. Yeah, okay, that is elementary step. For multi-step, right, it will be two or more steps. So different steps will have different rate. And the rate of overall reaction will determined by the rate determining step. So what is rate determining step? It is the slowest step in the reaction mechanism which determines the overall reaction rate. So it is in step with the highest activation energy. So you expect the slower step to have the highest EA. So in a reaction mechanism, it's important to state what is the slow and what is the fast step. Okay, like this. So this is the rate equation. So we can see that, hey, NO2, NO2, NO3, NO is slow. So this is slow. So this is a rate determining step, which have the highest EA. Then step 2 is the same as the example I showed earlier, NO3. Then NO3 is consumed in the second step and doesn't appear anymore at the end of step 2. So it will not be in the overall stoichiometric equation. Okay, so the overall equation, just take this plus this, you will have NO2 plus CO, NO plus CO2. So the NO3 is cancelled off. NO2 is 2 NO2 plus NO2. So one of the NO2 is cancelled off here, become NO2 on the left-hand side. So it's just equation 1 plus equation to get the overall. Now, so in order to derive the rate equation, we have to have this criteria to propose the reaction mechanism. Number 1, it must agree with the stoichiometric equation. So the elementary steps must sum up to give the overall equation such that the intermediate do not appear. And it must be consistent with the observed kinetics, agreed with the rate equation obtained. Okay? Now, so given a reaction mechanism, the rate equation can be deduced. There are 2 main situations to consider. So consider the reaction mechanism with step 1 as the slow step. Okay? Then the rate equation for the overall reaction can be deduced starting from the slow step. So the reactants that participate in the slow step are those reactants that appear in the rate equation. So the order of reaction with respect to reactant X is the number of X particles that participate in the slow step. So N2O is a reactant that appears in the slow step, and N2O must appear in the rate equation. Because it is in the slow step, so it is the reactant that will appear in the rate equation. And there is only one N2O molecule reacting in the slow step. So the order of reaction with respect to N2O is 1. So from the slow step, the rate of reaction is directly proportional to the concentration. Okay, because there's only 1, and this is elementary step now. All right, slow step, sorry. So we can just derive the rate equation directly. No, there's another N2O molecule participate in the fast step after the slow step, but does not appear. So, so because it appears in the fast step for N2O, so you cannot write the equation like this, cannot, because it is the fast step. So it is not, because the reaction is fast, it doesn't really affect the rate of reaction. If it's slow, there is room for improvement. There's room to increase the rate of reaction. But if it's already fast, then no point. There's not much you can improve on the speed of reaction. All right, so you don't consider the N2O in the fast step as part of the rate equation, cannot. O is an intermediate, so it won't appear in the equation at all. Now, reaction mechanism in which step 1 is not the slow step. So in this case, right, it will be the reactants in the step 2. Yeah. But NOCl2 seems to be the, but how come the rate? So from the slow step, they are directly based on just the slow step, you will write NOCl2 as well, right? But because it's an intermediate, right? So from step 1, you can see that. So how do you adjust it such that you don't want to see NOCl2? So the final rate equation, right, should not have the intermediate species that cannot have. So how do you accommodate with that? So you know that NOCl2 rate of formation is dependent on NO and Cl2, right? So NOCl2 is directly proportional to these 2. So the faster the formation of NOCl2, the faster NO and Cl2 reacts, correct? So instead of writing NOCl2, you put NO and Cl2, and then you just adjust accordingly. NO to the power 2, Cl2. This is a rate equation. So in this case, the reactants that appear in the rate equation are the reactants that participate in the slow step and reactants that participate in any fast step before the slow step. Because just remember, it should not show the intermediate, and you should equate to the reactants in the fast step in that case, okay? Now look at some example to further understand. So you have this reaction here. So deduce the rate equation given the reaction mechanism. Okay, a very familiar reaction. So step 1 is slow, Step 2 is fast, so you have H2O2, I minus from this, and this OI minus is the intermediate, plus more H plus, HOI also intermediate as well. Then HOI plus H plus I minus. Okay, how do you deduce? So the rate is just, so in the you just focus on this first, then you just write like that, the end. Because these two are fast step, forget it. Let's look at this one. Quite straightforward for this one. You just ignore the fast step for this example. Then for this one, you have this reaction a bit more complicated. So these are the steps. So you just focus on this first. But because these two they are you can tell that from the slow step, you write this first. But both are intermediate, so you need to equate them to others. So what to do? So the HBr is actually related to these two. So this one come to here, this one come to here, right? So you just put this first. And then step 2, this one actually come from these two. So you just add them together, H plus Br minus, H plus BrO3 minus. Then you put the H plus together, they will form this. Okay? You should not put the intermediate in the rate equation. That's it. Then you should equate them to the reactants that formed them previously in the previous steps. Now let's go to the theories of reaction rate. So we talk about what collision theory is very quickly because we have covered this in O level and some of your IP program. So I will just quickly glance through this. Okay, it's covered in O level already. So this is the collision theory. You can read yourself. And then they must collide with certain amount of energy, which means they must have energy equal or higher than EA in order for them to react. And activation energy is the energy barrel. This one you can just skip. Then, okay, this is a bit new. Transition state theory. So what is transition state theory? It's concerned with what actually happened during collision. So the theory picture the kinetic energy of particles changing to potential energy during a collision. So given a sufficiently energetic collision and the correct orientation, the species will become an unstable transition state or activator complex that exists as a potential energy maximum. So only reactant particles with adequate total energy can attain the critical configuration of this transition state. Okay, so in the transition state, right, is in the process of partial breaking of old bonds and formation of new bonds. So unlike a reactive intermediate, the transition state cannot be isolated. Once formed, the transition state can transform into its product. It can also be transformed back into the reactants. So the energy profile diagram depicts the changing energy of the chemical system as it progresses from reactants through transition state to product. So in a one-step reaction, there is one transition state. Okay, so the transition state, right, is at the energy, it's at the minimum amount of energy, right, to reach that. But of course, the actual energy could be more, but this is the minimum energy requirement to reach that state. Okay, and then it will then break the bond and then form the bonds, then form back the product. Sometimes reactions can happen in 2 steps. So reactants forming intermediate, which is the slow step, the rate determining step, and the intermediate forming the products, which is the fast step. So there are 2 transition states. So in this case, right, since the slow step is the rate determining step, you will expect the activation energy to be higher than the second one. It must be like that because slow step means slower, requires more energy. Okay. And then you have the second step, then forming the products. But the delta H is still like this, reactants to product. Okay, so that's about it, how you actually sketch the energy profile diagram. Now, we learned in the previous topic on energetics, okay, delta G indicates the thermodynamic feasibility. So if delta G is less than 0, is more likely to occur, but it's not related to kinetic feasibility. Kinetic feasibility is related to activation energy. So, give you an example. So you could have a situation where you have a thermodynamically spontaneous reaction based on delta G. Yes, But then it doesn't happen. Why? Because it's too slow. Why? Activation energy too high. Okay. So for example, diamond conversion to graphite based on delta G can happen because it's negative, but it doesn't happen in real life because it's kinetically not feasible or unfeasible because the EA involved is very high. So diamond is said to be kinetically stable, cannot become graphite easily. Another example is combustion of petrol. So it is supposed to be thermodynamically spontaneous by right, based on delta G, okay? But based on kinetics point of view, right, it's not kinetically feasible because petrol itself is kinetically stable. So in order to allow combustion to occur, we need to trigger it by a spark of flame to give it enough energy to allow reaction to proceed with enough energy to attain to reach EA, activation energy. So the EA involved in combustion is very high. You need a lot of energy for the reactant particles to achieve energy equal or higher than EA. Okay, this is the Maxwell-Boltzmann distribution curve that shows the distribution of particles at different molecular speed. So in the context of kinetic theory of gases, so for this is based on gases, okay, mostly. Because gases, particles are moving randomly, okay, in all directions at high speed. So it is used to talk about gases. So we know that gas have a large number of particles in rapid motion. Each particle will have a different speed. That's a concept. And every collision between particles will change the speed. That's why, because they will collide and then, not all collisions are elastic. So some will become faster, some will become slower. Yeah, so you have a range of distributions, okay, a distribution of speed. So at a particular temperature, the distribution of molecular speed will follow the Maxwell-Boltzmann distribution diagram shown here. So at low temperature, we will expect the distribution to be narrow with peak at low speed. Okay, but as temperature increases, right, the peak will decrease. And because it's spread out, the distribution broaden out to higher speed. Okay, so it's like, for example, let's say you have students who are not doing well. So most of them in the lower range, but as time progresses, right, they are more hardworking, they study harder, or they find the right method to study. You can see that the more and more people getting higher speed, getting better grades. So the distribution become narrow, how do I say, broaden out, rather, spread out the distribution, okay? So the kinetic energy of any particular molecule in a gas is always changing because there is always collisions, and that will cause change in speed and energy. So any instant, right, the distribution of KE, kinetic energy, is always constant under same condition. By right, same temperature, same average KE, okay? So the area beneath the curve is proportional to the total number of particles. Okay, and this is EA. So when the vertical axis, right, is changed to in terms of fraction, the total area will be 1. But this one will be total number. So just take note of what is labeled on the y-axis, okay? Now, so those molecules or particles that have enough energy to react upon collision, right, which means that collision is effective, will be here, the one shaded, okay? Those below cannot react upon collision. Now, so when the temperature increases, right, the maximum of the curve will displace to the right and take on a lower value, resulting in a greater spread of KE. The distribution curve broaden. KE is proportional to speed, okay? Now, the area under the curve is the same because the total number of particles remain the same. Please know how to sketch this. It will be coming out likely, okay? Please know this very well and indicate your EA as well. The EA will remain constant. So temperature increases, but EA is the same because it's still using the same catalyst. If the reaction is a catalyzed reaction. Then these are the factors that affect your reaction. I'm going to go through this very quickly. Okay, so the physical state. So reactant particles must meet in order for them to collide and react. So the frequency of collision will very much dependent on the physical state. So are the reactants in solution present as molecules or ions? So if you have this reaction is slow, because you have to understand why, because you have a CCl bonds here. This bond is of high bond energy, meaning high activation energy. So in order for this reaction to proceed, you need to supply sufficient heat to increase the temperature, to increase the rate of reaction, so that the particles have enough energy to react upon collision due to the high EA involved. And as for this one, right, in this case, right, if they actually, these two substances will dissociate or ionize in aqueous solution to form ions, right? So since the ions are opposite charge, they will have a natural tendency to attract because opposite charge attract. So, and in this reaction, there is no breaking of covalent bond. So activation energy is low. The reaction will occur instantaneously. So you don't need to supply additional heat. So the heat at room temperature will be sufficient for reaction to proceed quite quickly. How about this? So for this one, right, they are both in solid state. There will be no reaction. But for this one, right, you form a precipitate. It's a precipitation reaction, right? It has an immediate reaction here. So it depends on you have two solid or two solution. Two solution to form a precipitate is quite spontaneous. Okay, because the activation energy is lower. Here is higher because you need to break the bonds. Okay, then if the reactants is in solid state or finely divided state, of course the finely divided state will be faster because finely divided state means the total surface area is higher. So with a higher surface area per unit volume, the more contact it makes with the reactant, of course the reaction will be faster. Now, as for concentration, right, I'm not going to go through this in detail because you have covered this at O level. So basically, right, with higher concentration, reactants come closer together. Okay, there is more particles per unit volume. Okay, when that happens, there will be a frequency, the frequency of collision will increase. And also, right, you need to mention that the probability of collision having the correct collision geometry and sufficient energy will also increase because as they collide more, right, there's higher chance for the molecules to have the correct collision geometry and enough energy. So reaction rate will increase because frequency of effective collision. Remember, effective collision involves the right molecular geometry. So with more collisions per unit time, you will expect more chance or higher probability of correct collision geometry. How about partial pressure? So pressure have a negligible effect on the volume of solid liquid. So we only talk about gases. Okay, we only focus on gases, okay? Because it has negligible effect on the other two states. So partial pressure is a measure of concentration. So if you increase the pressure of a gaseous system, you're increasing the concentration because when pressure increases, right, the volume decreases. So you are making the molecules, right, come closer together. That will increase the concentration. So pressure and concentration are related. In fact, they are directly proportional given the same temperature based on the ideal gas equation. If you can look at the derivation here. So it follows that the rate of reaction is greater at higher pressure because they come closer together. There's higher frequency of collision. So because of that, higher probability of collision having the correct collision geometry and sufficient energy. So higher frequency of effective collision. As for temperature, we will just focus on how temperature affects the Maxwell-Boltzmann distribution of the kinetic energy. So the rate of reaction will roughly double for every 10 Kelvin rise or 10 degrees Celsius rise. So the change in temperature in degrees Celsius and Kelvin is the same if you talk about change. So it's either 10 Kelvin or 10 degrees Celsius, it's fine. So that will cause the reaction to double based on some studies. So increase in temperature, increase the average KE. So more reactant particles have energy greater or equal to EA. So you see a larger shaded area. Just show it differently, okay? So this result increase in effective collision frequency and increase rate of reaction. And also can talk about larger rate constant as well. That will increase the rate of reaction, which introduce us to the Arrhenius equation. Okay, so what is it? It relates rate constant to EA and temperature. So A is the Arrhenius constant, which should be given. EA is the activation energy. R is molar gas constant, which you can derive from the data booklet 8.314. Temperature in Kelvin, must be in Kelvin. And so this is the Arrhenius equation, which relates temperature to K. So when temperature increase or activation energy decreases, right, rate constant will increase based on the equation. So if we look at the graph of reaction rate against temperature for different types of reaction, so as temperature increase, the rate should increase exponentially. Explosive will be not so fast, but starting very fast because you need some time. You need a spark to initiate. Enzyme catalyze will be like this. We'll talk about that later. So what is a catalyst? It will increase the rate of reaction, but it will have no permanent chemical change. It remains chemically unchanged. So it's like it's involved in reaction, but at the end of reaction, it will be generated. So how does a catalyst increases the rate of reaction? So we look at the Maxwell-Boltzmann distribution of the kinetic energy, right? So basically, right, the catalyst will increase the reaction by providing an alternative reaction pathway of a lower EA. Please do not say lower the EA. It will provide a different alternative pathway of lower EA. So with a catalyzed reaction, the EA is lower compared to the original. Okay, and because of that, more reactant molecules have energy greater than or equal to activation energy for the catalyzed reaction. So you shade it differently. So here is like that, the other is like that. So for this one, right, it's different from just now the temperature effect on the Maxwell distribution curve. Temperature is more people work harder, then you have a broader range, right? But here is you lower the passing mark, so more people can pass. But it doesn't mean that more particles increase in speed. No, it's not that. So this is different. This is lowering the requirement. Okay, so I'm sure you have understood how the catalysts work and how it affects the EA, so I will not go to that. The rest of it you can read yourself, and this is the energy profile. Then let's go on to more on catalysts. So catalysts, there are some terms that are going to use it, like inhibitor is something that will decrease the rate of reaction. So the opposite of catalyst, inhibitor. Yeah, there's such a substance. Promoter means there's already a catalyst in place, but the promoter is there to enhance it further. Okay. Catalyst poison means it will inhibit the effectiveness of a catalyst. So it will directly attack the catalyst to make it less effective. There are two types of catalysts. One is catalyst is the plural, catalyst is singular. Okay. So homogeneous means the reactants and catalysts in the same phase, both liquid, both gases. Heterogeneous means the catalyst, right, is of different physical phase. Maybe the catalyst is solid state, the reactant is in gaseous state. So these are just some of the examples. You will need to know only some of them. Yeah, only some of them, not all. Okay, when we talk about organic reactions later, we talk about Haber process. Also, I think you learned some of it in O level also already. So for homogeneous catalyst, right, this is just example to illustrate. So what does a catalyst do is that CT represent catalyst. So you have the catalyst involved, but it is normally, it will convert one of the reactant to an intermediate. Okay, and then the intermediate react with another reactant to form the product, and the catalyst regenerated. And the overall equation, as I said, mentioned just now, you won't see the catalyst, you won't see the intermediate, which is the catalyst. So one example is this one. So in the uncatalyzed reaction, there's a direct reaction between the two similarly charged ions because they are both negative charge, so there will be repulsion. So the activation energy will be super high. So you definitely need a catalyst to ensure a faster rate of reaction. So what they do is that they add Fe3 plus. You remember, transition metals are good catalysts. They make good catalysts because they have these characteristics. They have variable oxidation state in their compounds, right? So because they can change from one oxidation to another, they can be used in such reaction. So for example, iodide cannot react with S2OA2 minus directly because repulsion between the similar charged ions. Your Fe3 plus can come in, which is of different charge to I minus. So this will help to lower the EA, meaning it allows the reaction to proceed in a different pathway than this. Instead of going this way, you're going another way, which also produce the same products, okay, more effectively at a lower rate, okay. So what happens is that the Fe3 plus react with this one form Fe2 plus. Then the Fe2 plus form react with the thiosulfate. So you have an opposite charge catalyst to attack the reactant separately, okay. And Fe3 plus is generated and go back and attack more iodide or react with more iodide. And you form iodine and SO42 minus, the ideal products you want. Okay. So that's it. So this is what I mentioned. Transition metal ions are very effective homogeneous catalysts because they have different oxidation state and they undergo conversion from one state to another very easily. So this helps to facilitate formation or decomposition of intermediate form in the reactions. Another example is the catalytic oxidation of atmospheric SO2 by oxides of nitrogen. So SO2 plus O2. This reaction, right, is very slow without a catalyst. It can be done, but very slow. So NO2 present in atmosphere will do something. It will act as a catalyst. So SO2 first react with NO2 to form SO3 and NO. And this NO involved in step 2 to react with the other reactant. So the catalyst attack one reactant first, and then in the second step, it attack the other reactant, and they form NO2. So the overall equation, you will have NO2 regenerated. So it's not in the overall equation because it's regenerated, right? Yeah. So you have SO2 become SO3 lah, if you combine these two together. Okay. So you can successfully oxidize SO2 to SO3 and have the NO2 regenerated to continue to oxidize further SO2 very quickly because it get regenerated and go on and on and on and on. And SO2 continue to be oxidized, and then it will react with water to form your sulfuric acid. Therefore, if you have NO2 and SO2, it's very, very bad because NO2 will be a catalyst for the oxidation of SO2, which will form the acid rain. Yep. Now, so this is the energy profile of a catalyzed reaction versus this is catalyzed. The one with two steps is the catalyzed one. One step is uncatalyzed. It's so high, the EA, very high. So instead of having such a high EA, you just replace with two smaller EA, more effective, right? Yeah, and normally the first step is, you see higher means what? So this one, right? Let's say this is the reaction, right? Then this is the slow. Obviously, the first one is a slow step. This is a fast step. Slow, fast. So the slow step is the, having a higher EA. Okay. Now, for heterogeneous catalysts, as mentioned, the catalysts and reactants are different state. So the mechanism is a bit different. Okay. So you have the reactant molecules readily absorb onto the catalyst surface. Absorb, not absorb, absorb AD. Yeah. So there was formation of weak bonds between the catalyst surface active site and the reactant molecules. So the reactant molecules is absorbed on the catalyst surface will increase the reaction rate because, okay, it will help to weaken the covalent bond within the reactant molecule. So when the reactant molecules are absorbed to the catalyst, right, the bonds between the reactant molecule itself is weakened. And this helps to lower the EA. And also the concentration of reactant molecules at the surface of catalyst will increase. This allow more, because you bring the molecules together at the catalyst surface, so you allow the molecules to come into close contact for proper orientation. So for example, H2 plus alkene form the compound. So this is the mechanism. First, you have diffusion taking place. The reactant molecules will diffuse towards the catalyst surface, where the reactant molecules are absorbed onto the active site by van der Waals forces. This increases the local concentration of reactants. So the reactants, because they come to the surface, you get more and more and more. And when that happens, right, it also at the same time, right, weakens the covalent bond within the molecule. So you make the EA lower. So the adjacent molecules, right, will just react to form the product. So bonds break between here, bonds form, something like that. Okay. Bonds break, the double bond break between the carbon, and it forms bond to CH. Okay, transition state. Then there'll be desorption, which is the reverse of adsorption. Okay, where the product molecules is formed and break free from the catalyst surface, and another reactant molecule can come onto the surface of the catalyst and repeat the process. Okay. So this is one example, the Haber process using finely divided iron as the catalyst. Then this is what we have learned in O-level, so catalytic converter, right? More detail, like it's actually coated with platinum, palladium, and rhodium. So they are the catalysts involved in the catalytic converter. So it's in honeycomb structure to maximize surface area for reactions. And then, okay, this is what we have learned before. NOCO, they will undergo redox reaction to form CO2 and N2. Either you can use rhodium. Then, rhodium is involved in the first step. So the NO or NO2, either NO or NO2 okay? Either that will both become the same products okay? Then the CO, okay, CO will also be oxidized with platinum or palladium as the catalyst. As for the combustion, will be these two, the unburned hydrocarbons. So it helps to convert them to less harmful products. However, if there is lead, it will poison or deactivate the catalyst, make it less effective, because the lead will occupy the active site. So when this active site is occupied, right, the molecules cannot be absorbed successfully. Autocatalysis. So it's a type of action where the product itself is a catalyst. So it's called autocatalytic. For example, this reaction. So how do you know that a reaction is autocatalytic? If you see that somehow the reaction initially like this, and then like this, like initially is slow then suddenly when more Mn2 plus form, it suddenly becomes fast. So it's not like a gradual change like this that you normally see, right? But you see something like this, is confirmed autolytic. Because so they ask you, what could have happened? Answer, the product is a catalyst. So as a catalyst form, it increases the rate of reaction by acting as an autocatalyst. Okay? But towards the end, right, because the reactant concentration also fall, so even if there is a catalyst, also no use, the rate of reaction will still decrease. The rate, right, is just, if you convert this to this, it will look something like that. Okay, this is another example. So to know something that, to prove that something is autocatalyst, right, you should add it at the start. If it is indeed autocatalyst, it will be super fast. Okay, last portion is on enzyme. Those who learn bio will have advantage. They are proteins, they are biological catalysts. Okay, we shall talk a bit more about enzyme in terms of active site. So the important part is the active site, because that's where absorption takes place. Okay, now enzymes are very effective and catalysts, and you do not need a large quantity. Actually, catalysts, you don't need a large quantity. A small amount will work to initiate reaction, to make reaction proceed very fast. Because the enzyme molecules are regenerated, and you can regenerate 1,000,000 times in 1 minute. So in general, enzymes are very specific to a particular reaction due to the three-dimension conformation. As for temperature, it operates most effectively at body temperature, but when it rises to above 50 to 60, it will cause a change in the 3D conformation. The enzyme becomes denatured or inactive. Okay, and enzymes are sensitive to pH. They only work within a narrow pH range. So if you change the pH too much, it will not work. It will be inactive. Okay. Then these are some properties of enzyme for those who are not familiar with, okay, who doesn't learn bio. Then enzyme, right, catalyze reaction by providing alternative pathway of lower EA. This one we learned that earlier on. It's something like catalyst, but it's a biological catalyst. But the way to do this is different. The enzyme will bind to the substrate to form an enzyme substrate complex, and then there'll be a reaction, and then new products are formed. New products will be will leave the active site. Enzymes are very specific, so a specific enzyme will only catalyze a certain reaction or bind to a certain substrate. So we use the lock and key model or induced fit model. For lock and key model, which the bio students are very familiar with, the substrate and enzyme have to be complementary shapes for them to fit nicely. So when brought together to a right alignment, right, the substrate will fit into the active site in the same way the key fits a lock and is bound by attractive forces on the active site. Then it will form an enzyme substrate complex, and this will weaken the bonding within the substrate. Of course, this takes place at a lower EA. So the enzyme substrate complex break apart. So the product form is no longer the right shape to remain the active site, and the enzyme is free to bind to another substrate molecule. So something like that. Okay, so it needs to be well fitted. The shape had to be complementary, like lock and key like that. Okay, in this case, this will be the lock. This will be the key to fit into the lock. Okay. For induced fit, right, it's different. The binding of the correct substrate induce a conformation change. So when the substrate comes in, right, the enzyme, right, will change to accommodate, okay, so that it will fit. But of course, if the binding of the correct substrate will fit well, but if you bring the wrong substrate, it will be still bind, but in the wrong place. Yeah, it's called induced fit model. So once you bind, then there'll be a change but if it's not the right substrate, it will not bring about any change. Yeah. So in the enzyme catalyzed reaction, the enzyme concentration should be very small compared to the substrate one. So the real reaction is just directly proportional. Higher, 2 times the concentration of enzyme, 2 times the rate. Okay? Yeah, because we assume that, substrate is very high in concentration relative to enzyme. So you just ignore substrate in this. As for substrate, right, when the substrate concentration increases, the rate of reaction will still increase, but at a decreasing, will still increase, but decreasing rate, getting smaller and smaller until it reaches a maximum. So at this point, right, when the substrate concentration is high, right, because why is it maximum? Because the active site is already saturated. You cannot fill out anymore. So further increase will not have any effect. So it will reach a maximum point. So for a fixed amount of enzyme, right, there is a finite number of active sites that can bind to the substrate. At low concentration, there's still unoccupied active site. So at this point, it's still quite linear. The order of reaction is first order. But very high, right, is 0 because it's already saturated. Okay, there's not enough active site to form, to bind to the substrate. Okay, cannot increase the reaction further. So lastly, right, these are just more examples. So you have the Haber process. So if the concentration of partial pressure NH3 is low, the order of reaction is first. Okay, because there's still available active site, not saturated yet. But when at moderate or high partial pressure NH3, right, it will be 0 order because active site are already taken out. There is, even if you increase the partial pressure further, it will not have any effect on the rate. Okay, that's it for the lesson. It's really very long and tedious because there's so many concepts, but it's really quite straightforward, just that there's a lot of concepts to go through. So I hope you will revise again at your own time. You really need to revise an important topic because it will definitely come out in your theory section and likely to come out in practical as well, because there is a, there is a practical session over there, planning, or you mean really do the kinetic study where you need to determine the order of reaction. Okay, so important topic. So thank you.